This is the second part of the electron configurations video. In part A, we looked at this first learning target. We explained the three principles that govern the ground state electron configurations. Recall those were the atom5b principle, the Pauli exclusion principle, and Hund's rule. And we'll be referring to those here in this video as well. The two learning targets we want to address here are numbers 11 and 12. We want to be able to write ground state electron configurations in spdf notation and noble gas notation. We also want to be able to draw ground state orbital box diagrams. So we'll just attack these one at a time here, working on writing ground state electron configurations first. Just recall from the previous video that a ground state electron configuration simply is the lowest possible energy arrangement of electrons in an atom. And what this does then is it determines the energy level, the sublevel, and the orbitals that the electrons for any atom, for any element, are found in. So just starting with some examples. Let's say we're asked to write the spdf electron configuration for oxygen. So if you look at the periodic table, you'll see that oxygen has atomic number 8. Recall that sometimes we see the symbol Z used for atomic numbers, so Z equals 8. So what that tells us then is in an oxygen atom, there are going to be 8 electrons, because in an atom we know that the atom is neutral, so there will be the same number of electrons as protons. The key here in writing this is we need to follow the atom5b principle, which, recall, that is simply the principle that says that electrons are going to fill the lowest energy orbital that's available. And we can determine that order based on the northeast to southwest rule, which is the same chart that you saw in the previous video. Recall, if we just follow each arrow, starting with the first arrow at the top and drawing in arrows diagonally from northeast to southwest, this gives us the order that the sublevels fill. So looking at this, we can see that the 1s sublevel is the first to fill, then the 2s, followed by the 2p, then the 3s, the 3p, the 4s, and so forth. So we can see from our diagram that the first sublevel to fill is 1s. So ask yourself, how many electrons can we put in a 1s, or any s sublevel for that matter? The answer, of course, is 2. So we can put 2 electrons in that 1s sublevel. So once there's 2 electrons there, we have to move on to the next sublevel. Well, looking at our diagram here, the 1s is filled. We go to the 2s. So the second sublevel to fill is the 2s. And again, ask yourself, how many electrons can we put there? Being that it's an s sublevel, 2 electrons is the max. So we can put 2 electrons in the 1s, 2 electrons in the 2s. So we're up to 4 electrons. So we always want to keep that in mind. That's 4 electrons we have so far. We need to have 8 total when we're done. So there's 4 electrons left to go. Well, the 2s is filled, so we need to look at what the next sublevel is. So we go to the next arrow, and it first cuts through the 2p. So the third sublevel to fill is the 2p. Ask yourself, how many electrons can we put in a p sublevel? Well, that answer is 6. But remember, there's only 4 electrons that we have left to go for this atom, because we already have 2 electrons in the 1s, 2 in the 2s, so that leaves 4 left, and that's all that will go in the 2p. So our electron configuration is actually written like this. We write 1s, like we normally would for that sublevel, and then we use a superscript 2. And what that tells us is that there are 2 electrons in the 1s sublevel. Likewise, we do the same thing for the 2s. Use a superscript 2 to show that there are 2 electrons in the 2s. And then we're putting 4 electrons in the 2p, so we use a superscript 4. When you read this, you don't read it as like math notation. You wouldn't say 1s squared. When you read this, you would simply read this as 1s2, 2s2, 2p4. You would not say 1s squared, 2s squared, 2p to the 4th. When we read electron configurations, we just read it straight from left to right. We just use the superscript notation to designate the electrons. The last thing you should do whenever you write an electron configuration, this is a great way to check your work, is to count up the electrons. Make sure that you have the right number of electrons. If we just look here, we're counting up, we have 2 plus 2 plus 4, that makes 8. And going back to what we originally had, we can see that we needed 8 electrons. So we probably did it correctly. Now we're asked to write the spdf electron configuration for magnesium. Magnesium has 12 electrons, so when all is said and done, we'll end up with 12 electrons in our configuration. Again, we're simply going to follow our northeast to southwest rule here. So the first sublevel to fill, that's the 1s, and as we know, we can put 2 electrons in an s sublevel. Then we go to the 2s, and again, an s sublevel, so 2 electrons. The third sublevel to fill is the 2p, and as we just mentioned in the last slide, we can put 6 electrons in a p sublevel. So let's just count up what we have here. We have 2 plus 2 is 4, plus 6 is 10, so we have 2 electrons left to go. Well, if we look at our chart here, after the 2p, we go to the 3s. So the fourth sublevel to fill is a 3s, and we can put 2 electrons in any s sublevel, and that's all the electrons, as we just said before. And if we count those up, that would give us 12. So our electron configuration we would write like this: 1s2, 2s2, 2p6, 3s2. And again, all those electrons add up to 12. Okay, next one. We're asked to write the spdf electron configuration for Krypton. If you look at the periodic table, you will see that Krypton has 36 electrons. 36 electrons. So from here on out in these examples, I'm just going to start by writing the electron configuration as you probably will whenever you're doing this. So we just start with 1s2 because the first sublevel to fill is 1s, and then we can see the next one is 2s, so 2s2. After the 2s is the 2p, so that would be 2p6. Following that arrow, that goes down to 3s, that would be 3s2. We're at the end of that arrow, so we go to the next one. The next sublevel to fill is 3p, so that's 3p6. Follow that arrow. The next sublevel to fill is 4s, so 4s2. Again, remember, s sublevels just can only have 2 electrons. After the 4s, we have the 3d. Okay, so notice here's the first time that we're seeing the orbitals overlap in sublevels from one energy level to the next. So even though the 3d is in the third energy level, it actually fills after the 4s because those orbitals have more energy. So if we just follow the arrows in this diagram, we can see that. Again, if you're not sure how we get that, we just follow this arrow here, 3p, through the 4s, and then we go to the next arrow, and that cuts through 3d. And recall that d orbitals, or d sublevels, can hold 10 electrons, so we can put in 10 electrons there. After 3d, we can go back to our chart here. We can see that's 4p, and we can put 6 electrons there. Now if you count this up, count up the number of electrons, you'll see that we have all of our electrons now. We have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36. And that's how many electrons Krypton would have. So there is the electron configuration for Krypton. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now before we go to any other examples, I just want to show you a periodic table here and show you how we can use a periodic table to get these electron configurations relatively quickly. Just to point out what this is showing you here. Notice that there are 4 different colors on the periodic table. On this one, you can see there's a blue here on the left, kind of a brown in the middle, a green on the right, and a purple on the bottom. These are referred to as the S, P, D, and F blocks respectively. And the reason why they're called that is because if you look at how this is labeled, these elements that are here in blue on the left, and notice they're labeled 1s, 2s, 3s, etc. These elements, their electron configurations all end with an s sublevel. Likewise, all these elements over here in green, they all end with a p sublevel. The ones in the middle, the brown here, they all end with an electron configuration in the d. And likewise, the purple here at the bottom, they all end with an electron configuration with an f sublevel. So just to show you what we've already done, how that coincides with this, recall with oxygen, and if you look back at that slide, you'll see that configuration ended with 2p4. Okay, and if you just count over on the p block, starting with boron, 1, 2, 3, 4, oxygen's 4 elements over on the p block, it will end with p4. Now we know it's 2p4 because it's in the second period here, and you can see this whole row here is labeled with 2p, and we can see that and it's 4 over, so it ends with 2p4. The next one we did was magnesium. Here's magnesium over here. It's in the S block, and notice it's in the third period, so it's going to end with the 3s sublevel. And notice that it's 2 over, starting with sodium, just counting over 1, 2. It's 2 elements over on the S block, so it'll end with 3s2. We then did Krypton. Here's Krypton over here at the end of the P block. It ended with 4p6 in our configuration, and if we count over on the P block, 1, 2, 3, 4, 5, 6, we can see that that's always going to be that way because it's 6 over in the P block. So these next few examples we're going to do here, I'm just going to give you the periodic table like we see here, and we'll refer to that along with the northeast to southwest rule chart. So we're asked to write the spdf electron configuration for nickel. So if we find nickel on the periodic table, here it is. We can see it's atomic number 28. Thus it has 28 electrons. And let's look at its position in the D block. Let's count over how many elements it is. So 1, 2, 3, 4, 5, 6, 7, 8. So what that tells us is nickel is going to have a configuration that ends with D8. And in this case, it's going to be 3d8 because it's in the fourth period, but notice it's 3d, and that's because of the overlap that we see. The 3d fills after the 4s. So the last thing that we're going to have filled here will be the 3d, and it will end with 3d8. Everything before that will be completely filled. So if you just follow the northeast to southwest rule chart up to 3d, filling everything completely full, and then putting in 8 electrons, because nickel's 8 over, then that will give you the correct electron configuration. So just filling that up, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. And all I've done is I followed this chart here. I've filled up every sublevel. Again, remember 2 electrons in S sublevels, 6 electrons in P sublevels. And when I got to the 3D, I put 8 electrons there because it's 8 over on the D block. Now if we count up the number of electrons, we'll see that there are in fact 28. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 8 is 28. So we probably have the correct configuration. Alright, same question here. We're doing an spdf electron configuration for tantalum. Tantalum is down here in the D block like nickel, but it's atomic number 73. Now let's look at what it should end with. Notice it is 1, 2, 3 elements over on the D block, so it'll end with D3, and it will end with 5D3. 5D3. It's in the 6th period, so it's going to end with 5D because remember the D's have an overlap. There is one, the 5D would fill after the 6S, so that's why the 5D is in the 6th period. So all we're going to do is we're simply going to fill up all the sublevels up to the 5D. So just follow the chart up to 5D, and then once you get there, just put in the 3 electrons because it's 1, 2, 3 elements over on the D block. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d3. So here's the first time we've ever seen an F sublevel in our configurations, and that just comes from our order here. We went through each arrow, we filled the 6s. If we go to the next arrow, that cuts through the 4f, so the 4f fills after the 6s. Recall we can put 14 electrons in an F sublevel. If we count up all these electrons, we will in fact get to 73. Okay, again, you want to count those up once you're done to make sure you've done it right. Alright, the next few examples are about noble gas notation. One thing you might be thinking is, well geez, for some of these elements that have a whole bunch of electrons, this can take a really long time to write these out and figure them out. And yeah, they can at first, when you're first starting to learn to do this, but there is a little bit of a shorter way to do it. In noble gas notation, we don't need to show all the electrons. So we're just going to start with an example. We're asked to write the noble gas electron configuration for phosphorus. So here's phosphorus on the periodic table. We can see it's atomic number 15. Whenever we write the electron configuration using noble gas notation, what we do is we look back to the previous noble gas. So going backwards on the periodic table, the previous noble gas we get to is neon, okay, when we go backwards from phosphorus. So what we do is we write the symbol for neon in brackets, and what that means is we're saying that phosphorus has neon's electron configuration plus whatever we write after it. Okay, and if we look at neon on the periodic table, we'll see it's at the end of the P block. It's going to end in P6, and neon specifically will end with 2P6. It'll end with 2P6 because it's in the second period. So all we're going to do with our electron configuration is we're just going to pick up after 2P. And then if we look at our chart here, the sublevel that fills after 2P is 3S. So we would write neon in brackets, and then we put 3S2, 3P3. And the reason I know it's 3P3 is phosphorus is 3 elements over, 1, 2, 3 on the P block. It's in the third period, so it will end with 3P3. As far as counting the electrons, here's what we can do. We can see that phosphorus, atomic number 15, has 5 more electrons than neon, which is atomic number 10. So if we count up our electrons that we have here, we have 2 plus 3, we're showing 5 electrons, so that is the correct number of electrons. Alright, next one. We're asked to write the noble gas electron configuration for zirconium. Zirconium is here on the D block. We can see it's atomic number 40. So if we're going to write the noble gas notation, we look back to the previous noble gas, which is Krypton. So we put Krypton, the symbol for Krypton, in brackets. And again, what that is telling us, we're saying zirconium has Krypton's electron configuration. So all these electrons that we would show, everything up to 4p6, that's what would be included in Krypton's configuration. Then we just show everything after that. So notice zirconium is 2 elements over on the D block, so it's going to end with 4d2. So all we're going to do is we're going to pick up with what goes after Krypton. Krypton ends with 4p6. So after 4p6, after 4p would be 5s2. And then we go to the next arrow, would be 4d. And as we said, it's going to end with 4d2. So 2 plus 2 is 4 electrons. And we can see zirconium, atomic number 40, has 4 more electrons than Krypton, atomic number 36. Next one, we're asked to write the noble gas electron configuration for radon. Now notice radon in itself is a noble gas. Now what you might be thinking is, well, why don't we just put the symbol for radon in brackets and call it good? Well, if you're doing a electron configuration for a noble gas using noble gas notation, you still go back to the previous noble gas. So the previous noble gas from radon is xenon. And xenon ends with 5p6. It's to the end of the 5th period on the P block. Radon is going to end with 6p6 because it's the end of the 6th period on the P block. So we look at our northeast to southwest rule chart. We can see that after 5p is 6s. So we have 6s2. And then just following our arrows here, we have 4f14. And then 5d10. And then 6p6. And if you count up the electrons, 2 plus 14 is 16, plus 10 is 26, plus 6 is 32. And if you count up the electrons here, we can see radon will have 32 more electrons than xenon. 86 minus 54 will be 32. Alright, last one here at the noble gas notation. We want to write the noble gas electron configuration for europium. Europium is down here on the D block. This is the first time we've seen one of these. Recall that the europium, even though it's down here pulled out, it's actually in the 6th period. So the previous noble gas to europium would be xenon. So we put xenon in brackets, and then we just pick up with everything after xenon's configuration. So xenon ends with 5p6. So I look at our chart here. After 5p is 6s. So we go 6s2. And then after the 6s is the 5f. And excuse me, 4f, not 5f. After 6s is 4f. I went to the wrong arrow there. 4f, 7. And if we count over, we can see that europium is 1, 2, 3, 4, 5, 6 elements over. You might be wondering why it's 4f7. Well, that's because we have to count the first element there, lanthanum, as well. So if we count that one, 1, 2, 3, 4, 5, 6, 7, we get our 7th spot. So there's the electron configuration for europium. Alright, so we've seen several examples of writing electron configurations in the full spdf notation and noble gas notation. And then what we now need to see is we need to draw some ground state orbital box diagrams. And we actually saw some examples of this in the last video using boxes and arrows. Recall that we just used boxes and arrows to represent the orbitals and electrons in an atom, respectively. And so it's just a simple example. Let's say we're asked to draw an orbital box diagram for beryllium. So all we're going to do is it's just like writing electron configuration. We start with the lowest energy sublevel, we work our way up. So we start with the 1s. Now any s sublevel has one orbital. So to represent that, we draw one box and we label it 1s. We then start putting in electrons. Well, beryllium has 4 electrons total. It's atomic number 4. So we're going to fill the 1s sublevel up. To show that, what we do is we draw an up arrow for the positive spin electron. Recall that 4th quantum number, the electron spin magnetic quantum number. That can either be positive or negative. So this would be the plus 1/2 spin. And then the next option is the down spin or the negative spin. So we draw a down arrow. So that 1s sublevel is filled. So now we go to the next sublevel, which would be 2s. And again, s's just have one orbital, so we draw one box. We've labeled it 2s. And then we'll have 2 electrons in this. And that's it, because beryllium only has 4 electrons. So the electron configuration would be 1s2, 2s2, if we were to write that out. Next example, draw an orbital box diagram for carbon. So if you look at the periodic table, you'll see carbon has 6 electrons. It's atomic number 6. But we'll always start with the 1s, even though it has more electrons than beryllium. And we can put 2 electrons in the 1s. So positive spin, negative spin. Then we'll go to the 2s, and we'd put positive spin, negative spin. So there's 4 electrons. After the 2s is the 2p. Now for a p sublevel, there are 3 orbitals in any p sublevel. So we draw 3 boxes, just like you see here. We label it 2p. Now there are 2 electrons left to go, because we have 6 electrons total. The first electron will always go in the first orbital with a positive spin, just like you see here. The question becomes, where do we put that next electron? Do we put it in the same orbital with a negative spin? Do we put it in a different orbital with a positive spin? Or do we put it in a different orbital with a negative spin? Well, the answer to that is to remember Hund's rule. Recall Hund's rule tells us that whenever we have degenerate orbitals, and these 3 orbitals here would be degenerate because they're all in the same sublevel, we always put 1 electron in each orbital first with the same spin before we pair up. So the next electron would go in that second orbital and it would have a positive spin, just like we see with that first electron in that sublevel. So there would be the the orbital box diagram for carbon. Okay, next example. Let's say we're asked to draw an orbital box diagram for vanadium. You can see I have the periodic table here on this slide, and just for reference here, here's vanadium. It's atomic number 23. Notice it's 3 elements over, 1, 2, 3 on the D block, so it's going to end with 3d3 because it's in the 4th period, but as we know the D sublevels, they overlap 1, so it'll end with 3d3. Everything before that will be all filled up. So we start at the 1s, 1 orbital, 2 electrons. Then we go to the 2s, 1 orbital, 2 electrons. Then is the 2p, and notice when I click through these here, I'm going to put one electron in each orbital first, all with positive spin, and then I'll pair them up with down spin. So now that sublevel is filled. Now I go to the 3s, so one orbital, two electrons. Then the 3p, and again we have one electron in each orbital first, and then we go to the negative spins to fill up that sublevel. After 3p is 4s, just one orbital, two electrons. Now after the 4s, this is where we have that overlap. We have the 3d come next. Now notice there are 5 orbitals, so we draw 5 boxes in for the d sublevel. As we said, this is going to end with 3d3 because it's 3 elements over on the d block. So those 3 electrons will go in each of the first 3 orbitals, all with positive spin. And there's the orbital box diagram for vanadium. Alright, draw an orbital box diagram for platinum. Notice here platinum has 78 electrons. So you might be thinking, wow, that's going to take me forever drawing all those boxes and electrons. Yeah, it could, but what you could do, and if you're ever asked to do this on a quiz or a test, I would tell you that you could specifically, you can use noble gas notation still, like we saw previously. So the noble gas notation from platinum would include xenon, because that's the previous noble gas, and we just pick up with the box diagram after xenon. So xenon would end with 5p6. After that, we would go to the 6s. So we have the 6s sublevel, one orbital, two electrons. After the 6s is 4f. Notice there are 7 boxes here for the 7 orbitals, and this would be all filled up. And again, each orbital will have one electron in it first, and then we'll start pairing them up with negative spins. Now a question you might have is, how do we know when to stop? Where are we going to stop with these boxes and electrons? Well, notice here platinum is going to end with 5d8. If I count over 1, 2, 3, 4, 5, 6, 7, 8, it's going to end with 5d8. The next sublevel to fill after 4f is 5d. And again, notice 5 boxes there for the 5 orbitals. And then there's going to be 8 electrons in it. So the first 5 are going to fill each of the first 5, or each of the 5 orbitals with a positive spin. And we still need 3 more. So those 3 are going to go back and start pairing up with negative spins. And there would be the orbital box diagram for platinum using noble gas notation. Alright, that's the end of the examples here. We've hit each learning target. The only way to get good at this is to practice. So we'll spend quite a bit of time in class practicing this stuff to give you a chance to really get good at all this stuff that you've seen here.